everyone, I'm Dr. Rizwana, working as a Professor of Physics in Institute of Aeronautical Engineering. Today I'm going to discuss about semiconductor devices. As we know that when we talk about semiconductors, these materials are special in their applications. And we know that these materials, when we talk about their conduction, they'll behave both as insulators as well as conductors. And because of their because of their exhibiting two types of characteristics, so that's why they have got many applications. So in the semiconductor devices, we'll just try to discuss some of the definitions and terms which will make us get familiarized with semiconductor devices. So here, starting with this, coming to our first definition here, what do we mean by generation of an electron hole pair? So first, when we talk about semiconductors, of course, we say that generally they are insulators, but they'll behave as conductors. So now, when they'll behave as conductors? So here, when we talk about their conductivity, so generally we talk in terms of generation of electron hole pair. So here we talk about generation of electron hole pair. So here, we know that generally when we talk about energy band diagram, so here when we talk in terms of energy levels, we'll take valence band, which is represented as, of course, in valence band, topmost energy level it is given by EV, and coming to conduction band, bottommost energy level it is given by EC. And here, of course, we know that this energy difference between bottommost energy level of conduction band and topmost energy level of valence band, it is equal to forbidden energy gap, which is equal to EC minus EV. And first of all, so when we take any atom, okay, or when we take semiconductors, generally suppose we know best examples for semiconductors are silicon and germanium. So if we take silicon, we know that either it can be silicon or it can be germanium. They belong to group 4. So here, generally this, if I take each silicon atom in a silicon crystal, it consists of 4 valence electrons. Out of those 4 valence electrons, it will form 4 covalent bonds with adjacent silicon atoms. So all the electrons, they are taking part in covalent bond formation. So here, generally we'll say that whenever electrons, they take part in covalent bond formation, because there are no free electrons, so that's why here they act as insulators. So here we can say that at this particular, and this occurs at temperature T is equal to 0 kelvins, and because there are no free electrons left out, so that's why we'll say that there are no electrons in the conduction band, and whatever valence electrons are there, because they are taking part in covalent bonds, we'll treat them as electrons in valence band. So we have electrons in valence band, those are nothing but valence electrons which are without energy. Now what we are going to see here is, now for these electrons, generally valence band of semiconductor, it is completely filled at T is equal to 0 kelvins, and when we supply external energy, and that energy, it can be in the form of temperature or it can be in the form of electric field. So when we supply that energy, then generally what happens to these bonds, these covalent bonds will break. So breaking of covalent bond takes place. So here we have breaking of covalent bond. So breaking of covalent bond takes place, and what exactly we mean by breaking of covalent bonds? It means that whatever electrons which are strongly bonded to their atoms, they'll come out of that bond and they'll be actively participating in conduction. So what happens to these valence electrons which are present in the valence band? They'll gain energy, and that energy, it is coming either as thermal energy or it can come as electrical energy. So these electrons, they'll take that energy, and of course that energy, it should be sufficient enough in order to make this electron which is present in the valence band to jump across the forbidden energy gap and go to conduction band. So we always, whichever energy we are supplying to those electrons in the valence band, it should be greater than or equal to Eg. Then only these electrons, they will take that external energy and they'll go to conduction band. So this transition is taking place. That is nothing but breaking of covalent bond. And for each transition, when one electron in valence band goes to conduction band, then one electron hole pair will be generated. So one electron hole pair will be generated. So here electron after taking energy, valence electron which is present in the valence band, after taking energy, when it goes to conduction band, then what happens in valence band? A hole will be generated, and here we'll have free electron. So for each transition, we are going to get one electron and one hole, and hole in valence band, electron in conduction band. And this particular phenomena, it is called as generation of an electron hole pair. And when we take intrinsic semiconductors, which are pure semiconductors, what we are going to observe here is, for each transition, we are going to get one electron hole pair. So that's why, depending upon number of transitions, so many number of electron hole pairs are generated. So only in case of intrinsic semiconductors, number of holes in valence band and number of free electrons in conduction band are equal in number. So this is about the generation process. Now coming to next question, what is a diode? So here generally, of course, we take it to be a diode, but generally if we try to see what exactly is a diode, its full name, it comes out to be PN junction diode. So diode is nothing but PN junction. So here, or simply it is also called as junction diode also, or simply of course diode. And generally what is the symbol for diode? In order to go for symbol, generally we'll draw one triangle followed by one vertical line. So this is our diode, and of course this triangle, it represents P type of PN junction, and this vertical line, it represents N type of PN junction. And generally this end, it will act as anode, and whereas the other end, which is towards the N type of PN junction, it will act as cathode. Of course, this is the symbol. And so what exactly, when we talk about diode, diode is nothing but combination of P type and N type semiconductors. So combination of P type and N type semiconductors is nothing but our diode. Okay, and of course, what happens when diode is formed? We know that there will be diffusion of charge carriers, that we are going to discuss in next definitions. But for the time being, what exactly we mean by diode? So when someone asks what is a diode, so diode, it is nothing but a PN junction where we are going to combine P type and N type semiconductors together. And when we talk about this P type and N type semiconductors, we know that in P type semiconductors, our majority charge carriers are holes, whereas in N type semiconductors, majority charge carriers are electrons. And this P-type semiconductors, they are formed by doping of travalent impurities to intrinsic semiconductors, whereas N-type semiconductors, they are formed by doping pentavalent impurities to intrinsic semiconductor. So this is about the diode, and there is one more way in order to define a diode. We can call it as a device, semiconductor device, which consists of two terminals. So you can make out it has two terminals, one end is anode and other one is cathode. And usually what we'll observe here is this diode, it will act as conductor when it is forward bias. So it is taken as if it is allowing the flow of current in one direction only, because in reverse bias mode, diode, it will not conduct any current and it will act as insulator. So we can also call diode as unilateral devices, so which will act as conductor only when it is forward biased. Now coming to next definition. Now we got familiar about generation of electron hole pair. Now we talk about recombination of electron hole pair, and this recombination process is completely opposite to generation process. So when we talk about recombination, so here when we take recombination process, in of course this is also called recombination of electron hole pair. So in this case, of course in generation our electron, it was there in the valence band, but in case of recombination, after we supply suitable form of energy to valence electrons in valence band, of course they'll go to conduction band. So now we have our electrons in conduction band. Now for how much time these electrons are going to stay in higher energy level, that is conduction band. So it will be for their lifetime. So these electrons which have gone to conduction band, they are going to stay in that band or in energy levels of conduction band for their lifetime. So once lifetime is over, so there are chances of this electron to come down back to its valence band. So what these electrons will do, these electrons will come back to their original vacant site which is present in the valence band. So electron losing its energy and then of course coming back to valence band, that process it is called as recombination. So here this is just like electron because it is coming back to its electron site. Suppose if it comes back to its original vacant site in valence band, then that phenomena it is called as direct recombination. Whereas when we talk about indirect recombination here, of course that electron it may not come back to its original vacant site, and here this case it occurs when our material it has got any like homogeneities or any defects. So here, so generally, so when we try to define recombination, so in recombination it's the reverse process. Reverse to what? Reverse to generation of electron hole pair where electron and holes, okay, and of course where these electrons are present in conduction band and holes are present in valence band, and both of them recombined and they get annihilate. So what do you mean by annihilating? Of course this is of course combination or becoming neutral. They are losing their energy. In generation, here we are going to see that electron and hole they are gaining energy and they'll take part in conduction. But whereas in recombination process, electron as well as hole, free electron and one free hole, they are going to lose their energy and they'll become immobile charge carriers. So they'll become neutral, they'll combine. So such phenomena it is called as recombination. And this recombination, of course we know that generation of electron hole pair it takes place when we supply external energy. But for recombination to takes place here, it can occur after lifetime of energy level in which electron is present, or sometimes will supply external energy in order to push this electron to valence band. So it can be spontaneous or it can be because of some external energy supplied. Now coming to next definition, what is a photodiode? Now here when we talk about photodiode, here we are talking about one of the very important optoelectronic device. So here I am referring to optoelectronic device. So it is one of the optoelectronic device, and of course we just now we have taken what exactly is a diode. We know that diode is where we combine p-type and n-type semiconductors, so they come together and they'll form p-n junction. So here, what exactly is photodiode? So photodiode, it is nothing but reverse bias diode. So same p-n junction or same diode which is made up of either silicon or germanium. And here what I am doing, I am reverse biasing it. Reverse biasing means where p-type of p-n junction, it is connected to negative terminal of battery, whereas n-type of p-n junction, it is connected to positive positive terminal of battery. So p-type of p-n junction, it is connected to negative terminal. N-type of p-n junction, it is connected to positive terminal. Then this particular, after reverse biasing, in photodiode, generally what we'll observe here is, we know that at the junction, there is a region where this p-type and n-type will be joining each other. So near the junction layer, we'll have one depletion layer. And this depletion layer, it is formed because of diffusion of electrons and holes across the p-n junction. And this depletion layer, which consists of immobile charge carriers. Now, as we know that we have here holes. Holes, they get attracted towards the negative terminal of battery, whereas these electrons, they get attracted towards the positive terminal of battery. And as a result, this depletion layer, it is going to increase when we reverse bias a diode. And whenever we are reverse biasing a diode, it will act as insulator. Okay, so but of course here we are saying insulator, but there will be some small leakage current. That current, it is because of minority charge carriers. And generally we'll say that current flowing in reverse bias p-n junction is nil. But what we are doing in photodiode, we know that when we reverse bias p-n junction diode, depletion layer, it is going to get increased. Now when I expose this depletion layer to high frequency radiation, so what I am doing, I am exposing this depletion layer to light radiation. Now this light radiation, we know that it consists of photons which are energetic. These photons, they are going to collide with immobile charge carriers in depletion layer, and they give their energy to those immobile charge carriers and they'll make them move and participate in conduction. So here what generally is happening, photodiode, it's a device in which we are making a reverse biased diode a conductor. Generally it's an insulator, but we are increasing reverse current. Okay, and that intensity of this magnitude of reverse current, it is dependent on what is the intensity of light radiation falling on this depletion layer. So what is my input here? So when we talk about this reverse biasing, of course it won't act as our input. Our main input is our light radiation. And what is our output? We know that when this light radiation falls on these charge carriers, they'll become mobile, they'll take part in conduction. It means that we are increasing our reverse current. So my output is reverse current, which is nothing but electrical energy. So what this photodiode is doing, it's an optoelectronic device whose input is light radiation and whose output is increase in reverse current. So here we can say that photodiode is a semiconductor device that converts light into an electrical current. And the current is generated when photons are absorbed by immobile charge carriers which are present in the depletion layer of reverse biased photodiode. Then coming to next definition, define LED. So we know that LED, we must have seen LED in our day-to-day life. So now everywhere, instead of making use of those small bulbs, we are making use of LED, and of course we have our LED TVs. Okay, so there are many applications when we talk about LED, and these LEDs also, they will come under optoelectronic devices. This is also one type of optoelectronic device. And coming to LED, what is the full form of LED? LED, it is taken as light emitting diode. So it is called as light emitting diode. And this LED, it is completely opposite to photodiode. So it is completely opposite to photodiode. We know that our photodiode is reverse biased. But coming to LED, of course, here we'll take our diode, which is nothing but our PN junction. So this is our PN junction, and this PN junction, what we are doing, we are forward biasing it. So forward biasing means where P type of PN junction, it is connected to positive terminal of battery, and N type of PN junction, it is connected to negative terminal of battery. And when we talk about this PN junction, it is not made with general silicon or germanium semiconductors, but they are made with some special type of semiconductors which are called as direct band gap semiconductors. So these are direct band gap semiconductors, and there is another name for this direct band gap semiconductors. They are also called as compound semiconductors. So they are called as compound semiconductors. And generally what we are going to do here is we'll take different elements from different groups. I'm going to make one compound semiconductor by combining elements from third group as well as fifth group. Or I'll take one element from second group and another element from sixth group. Or I can combine two elements coming from fourth group. So when I go for such combinations, I'm going to get our direct band gap semiconductors. And what is the specialty of these direct band gap semiconductors? In direct band gap semiconductors, energy gap, which is difference between energies of bottommost energy level of conduction band and topmost energy level of valence band. So this difference, it is equal to h nu, which is energy of photon. And here what we are going to observe here is, in this case, because we are forward biasing this PN junction, which is made with this special type of semiconductors, we know that in P type we have lot of holes, in N type we have lot of electrons, and these holes, because of their repulsion from positive terminal of battery, they'll move towards the depletion layer. Similarly, electrons also move towards the depletion layer, and here generally what will happen here, recombination process is taking place where hole and electrons, they'll recombine, so they'll lose their energy, and that energy, it is coming out in the form of photons, because forbidden energy gap is equal to h nu, because we have selected materials called as direct band gap semiconductors. Here direct recombination taking place where electron in the conduction band, it will come back to its original vacant site, or we can also say that minimum value of momentum vector k in conduction band, it is equal to maximum value of momentum vector in valence band. So and here energy, it will be released, and that energy, it is coming out in the form of photons. So what is our input here? Our input is forward biasing, which is electrical energy. And what is the output we are getting? Our output energy is light energy, which is coming in the form of the photons. So we can say that light emitting diode, It's an optoelectronic device which is going to convert electrical energy into light energy. And one more thing, so when we talk about symbols, so we have taken diode symbol like this. And here just now I have explained about photodiode. So when we consider symbol for photodiode, of course we'll take a symbol of normal diode. And what is the input we are giving? Input we are giving light. So this symbol it is for photodiode. Whereas when we talk about light emitting diode, we know that from this diode, light will come out. So what is the symbol for LED? This is the symbol where we are showing that light is being emitted out. So this is the symbol for light emitting diode. So one thing what we have to understand here is, of course, apart from saying that light emitting diode, it will convert electrical energy into light energy. We can also say that it's a forward bias PN junction diode made with special type of semiconductors called as direct band gap semiconductors, where energy is being released in the form of the photons. Okay, so as you can see, this is also semiconductor device that emits visible light when electric current passes through it. And when electric current passes, when you forward bias this PN junction. The next is, what is a photodetector? So we have seen what is a photodiode. Now we are talking about photodetector. So what is photodetector? Photodetector, of course, it's a PN junction, and this detector, it is sensitive to light. So what do you mean by being sensitive to light? Once light falls on this photodetector, then automatically what it will do, it will send us output signals in the form of current. So it will send us electrical signals. So it is going to convert light photons into current. So moving further, for some more definitions, here if we see, here we have defined conduction band. So as we know that what exactly is a band? Band is nothing but collection of energy levels. So when we talk about energy band diagram, so generally this energy band diagram, it is taken like this. And this one, of course, each band, it is made up of many energy levels. The set of such continuous or series of energy levels which are very close to each other, that set of energy levels, it is called as band, energy band. And when we talk about energy bands, there are two allowed energy bands and one forbidden energy band. And those two allowed energy bands in which electrons can exist are nothing but our valence and conduction band. Whereas energy band in which electron cannot exist, that band it is called as forbidden energy band. And here you can see this lowermost band is our valence band. This is our conduction band. So what is our conduction band? Conduction band is nothing but higher permitted band, and it will consist of free electrons. So when I say that there are electrons in valence band, it means that I am talking about electrons which are taking part in conduction. And depending upon what type of material we are selecting, we can have this conduction band either partially filled or it can be empty also. So it will be empty in case of insulators, whereas it is, of course, it is full. It will have more number of electrons when we talk about conductors. So generally, so we can say that it is the least filled higher permitted band in which electrons can move freely and they will take part in conduction. Then coming to next one, forbidden energy gap. So as you can see in this energy band diagram, so this bottommost energy band, it is called as valence band, and this topmost energy band, it is called as conduction band. And this valence band and conduction band, they are separated by one more energy band. So this energy band, it is represented by Eg, which is called as forbidden energy gap. And here electron does not exist in forbidden energy gap. When we supply electrons to valence band, they'll take that energy and they'll jump across the forbidden energy gap and will go to conduction band. So, or we can also define as this forbidden energy, it is also defined as energy required to transfer an electron from valence band to conduction band, or energy required to make a immobile electron. A mobile electron is nothing but forbidden energy gap. The next is what is a conductor. So when we talk about conductor, again we'll take help of this energy band diagram. So if you see this forbidden energy gap, depending upon width of forbidden energy gap, of course we have three types of materials: conductor, insulators and semiconductors. So when we talk about conductors, if we see here, in case of conductors, and of course this is our valence band and this is our conduction band. And when we talk about conductors, generally we'll say that there is no forbidden energy gap. So this is our valence band and this is our conduction band. And here we have series of energy levels. Valence band also we have series of energy levels. Now as you can see, there is no forbidden energy gap. What does it indicate? It means that electrons which are present in the valence band or valence electrons, these valence electrons. So here if you see, so if you take this valence electrons, they don't need any energy to go to conduction band. So generally these valence electrons, what they'll do, easily they'll flow from valence band to conduction band. We don't have to supply energy, and best example for conductors are metals. So if we take metals, we know that in metals, they are good conductors of electricity and there are abundance of free electrons. Electrons just they'll be wandering from one atom to another atom. So they are not fixed. Valence electrons of an atom, they are not just fixed to that atom, but they'll be moving from one atom to another atom. Then next we have insulator. What is an insulator? Again, when we talk in terms of energy band diagram, so in case of insulator, so here till now we were talking about conductor. So when we talk about insulator, again we'll try to take width of forbidden energy gap, and what we'll say that in case of insulator, width of forbidden energy gap, so which is Eg. This Eg is very wide. So Eg is wide. So what do you mean by Eg being wide? It means that width of forbidden energy gap is very wide. So in order to make a valence electron a free electron, we need to supply very large amount of energy. But once we apply large amount of energy, what happens to material? Material will get destroyed. So we cannot make an insulator conductor. Okay, so in insulators, we'll say that band gap between valence band and conduction band is so large that electrons, they cannot take energy and jump from valence band to conduction band. Then talking about our semiconductors, which is our main material of consideration. In case of semiconductors, so what we are going to observe here is this width of forbidden energy gap is very, very small. So this Eg, it is very small. So Eg is small. It means that once we have here also first, if I take semiconductors like silicon and germanium, their valence band is completely filled, but when I supply small amount of energy, what happens to these electrons? They'll easily jump across the forbidden energy gap and they'll go to conduction band. And once these electrons take transition to conduction band, here in valence band we have generation of another type of charge carriers which are called as holes. So we'll have holes in valence band and here we have free electrons in conduction band. And talking about this hole, we'll say that they are positively charged. And of course they also take part in conduction. So when we talk about conductors, we'll say that conduction is mainly due to electrons. And when we talk about insulators, we'll say that there are no charge carriers at all. But when we talk about semiconductors, there are two types of charge carriers. One type, there are holes, and another type, there are electrons. And because of this two type of charge carriers, they have got many applications. Then next, explain the meaning of an intrinsic semiconductor. So generally when we take intrinsic semiconductor, when we talk about intrinsic semiconductor, we'll say that these are pure semiconductors. So we'll say that they are pure semiconductors which does not have any impurities, right? And the best example of intrinsic semiconductors are our elemental semiconductors which belong to group 4. So here we have silicon and germanium. And when we take these intrinsic semiconductors, generally at T is equal to 0 kelvins, they are insulators. Why? Because whatever valence electrons are there, they are taking part in covalent bond. So that's why there are no free electrons. So at T is equal to 0 kelvins, they are insulators. But what I am doing to these semiconductors, I am supplying temperature and heating it. So when I go to T 0 kelvins, greater than 0 kelvins, what happens to those covalent bonds? They will break. And generally generation of electron hole pair takes place. So whatever electrons which are present in the valence band, they'll jump across the forbidden energy gap and they'll go to conduction band. As a result, there will be creation of two types of charge carriers which are electrons and holes. Now coming to next definitions. Here, of course, what is a hole? So just now we were talking about generation of hole. How hole is generated? So when we talk about generation of electron hole pair, so here this is our conduction band and this is our valence band. First, when we are not supplying any energy or electron, it will be in valence band, but when we supply energy, then this electron which is present in the valence band takes that energy and it will go to conduction band. It means that there is some vacant site because it has gone to conduction band. This electron, it has left valence band, it has gone to conduction band, and this vacant electron site is nothing but hole. Okay, and generally when we talk about a hole, we'll say that it is positively charged. So hole is positively charged, and it will also take part in conduction, and generally they are present in valence band. And one more thing is, of course, we say that these holes are taking part in conduction. It means that once vacant site is created here, it will be filled by electron of adjacent atom. Again, now what happens to hole? Hole is here. Again, this hole, it is being filled by electron of adjacent atom. So this process continues as if hole is moving from one place to another place. And whole concept, it is completely imaginary concept, and physically speaking, hole does not exist. But in order to explain some of the properties exhibited by semiconductors, we are treating these holes, vacant electron site, as a hole, and will take it to be a positively charged. Now next one is describe about extrinsic semiconductors. So we have seen that in intrinsic semiconductors, they are pure semiconductors which does not have any impurities. But when we talk about extrinsic semiconductors, generally we'll take intrinsic semiconductors like silicon and germanium, and then we'll dope them with impurities. So depending upon what type of impurity we are doping, there are two types of extrinsic semiconductors. One is p-type, another one is n-type. So generally when we say that what are extrinsic semiconductors, we can say that these are impure semiconductors where impurities are added to intrinsic semiconductors. And what is our intention behind adding impurities? Our intention is to increase charge carriers. See here, in intrinsic semiconductors, by increasing temperatures, we are increasing charge carriers. But in what way extrinsic semiconductors are different from intrinsic semiconductors? So in extrinsic semiconductors, what we'll do, without going to high temperatures, we can get free charge carriers at low temperatures by doping them with different impurities. Then next we have n-type semiconductors. So as I told you, we'll take intrinsic semiconductors and we'll dope them with impurities, and depending upon what type of impurity we are doping, suppose if we are doping group 5 elements, so group 5 elements, they are called as pentavalent impurities. So group 5 elements, they are called as pentavalent impurities. If we dope intrinsic semiconductors with pentavalent impurities, such type of semiconductors, they are called as n-type semiconductors. And in n-type semiconductors, what are the majority charge carrier? Majority charge carriers are electrons. So, and these pentavalent impurities, they are called as donor impurities because they are donating their electrons to conduction band of intrinsic semiconductor. Similarly, when we talk about p-type semiconductors, completely opposite to n-type, we have p-type semiconductors, and here we are going to dope group 3rd elements, okay, which consists of 3 valence electrons, and these are called as of course travalent impurities. Okay, examples we can take boron, aluminum, gallium. And when we talk about pentavalent impurities, we can take arsenic, antimony, phosphorus. And coming back to our group 3 elements, so what happens when we add group 3 elements, then what we are going to observe here is these impurities, travalent impurities, they are called as acceptor impurities. And these impurities, they have this tendency of become negatively ionized by accepting electron from valence band of intrinsic semiconductor. So as a result, what they'll do, of course, because they're accepting electron, they'll give hole, they'll result in the formation of hole in valence band of intrinsic semiconductor. So that's why here majority charge carriers are holes. Then of course we have generation of electron hole pair, where electron which is present in the valence band, it will absorb energy and it will go to conduction band. And of course we have taken recombination also. Then next we have potential barrier. So what is potential barrier? We know that once we form PN junction where we are going to combine P-type and N-type semiconductors, we know that in P side we have lot of holes, whereas in N side we have very small concentration of holes. And again in N-type we have a majority of electrons, where in P-type we have very small number of electrons. So there is a change in the concentration of charge carriers. So that's why what we are going to observe here is holes, they'll try to get diffused from P side to N side. And similarly, electrons, they try to get diffused from N side to P side. In this process, it is called as diffusion process. What is diffusion? Where we have flow of charge carriers from higher concentration to lower concentration region. And once this diffusion takes place, and once hole from P side, when it goes to N side, it is going to give its energy to electron, then it will become positive, immobile positive ions. So here we have collection of immobile positive ions towards the inside of PN junction. Similarly, once electron in inside, if it goes to P side, it is going to give its energy to hole, and it is going to form negative, immobile negative ion towards the P side. And because of accumulation of these immobile ions, here one potential barrier, one voltage is created, which is going to stop further diffusion of charge carriers, and this voltage created, that is nothing but our potential barrier. So what is potential barrier? It is the region in which we have decelerated atoms, decelerated charge carriers, where there are charge carriers without any energy. Also, we can say that it is depleted of charge carriers. And what is the role played by this potential barrier? It is going to prevent further diffusion of charge carriers across the junction region. Now, what is the level that acts as a reference which separates vacant and filled state? That is nothing but Fermi level. So here we know that when we take a band, so generally if we take any band, it is made up of many energy levels. And of these energy levels, some energy levels are completely filled and some energy levels are empty. Now suppose I have these energy levels filled with electrons. Now why I am putting 2 electrons per energy state, energy level? Because we know that not more than 2 electrons can exist in an energy level. Now here there exists one energy level. That energy level we are taking it to be EF, and this energy level is the boundary energy level which is going to separate. So as you can see, these are filled energy levels and these are empty energy levels. And this definition, it is valid only at temperature T is equal to 0 Kelvin. So what is that energy level called as? Fermi energy level. Then next, which of the following theories can be adopted to rectify the drawbacks of classical theory? We know that there are certain drawbacks of classical theory. So in order to overcome, first we'll see what are the drawbacks. So if you take classical theory, it could not, of course it can explain properties of metal. So where it treats free electrons in metal as molecules of gas. So it talks about electrical, thermal conductivity, and as well as, of course, the properties of different metals. But there are some drawbacks which are related to classical theory. So in order to overcome them, then came our quantum theory. We have our quantum theory, of course, our band theory, which will try to rectify the drawbacks of classical theory. Now, which of the following theories cannot be explained by, of course, classical theory? As we know that this classical theory could not explain about this insulators and semiconductors. And also, it could not explain about photoelectric effect, also phenomena of photoelectric effect. Then here, what happens to free electrons when electric field is applied? So if you take in metal, we know that in metal, electrons are moving in all possible directions, so with all possible velocities. But when these electrons are moving randomly in all possible directions, so they are moving and they are colliding with each other. But to such electrons, if we apply electric field, then we'll observe that all these electrons, they'll start moving in one particular direction. So they are going to gain velocity in one particular direction, and that velocity is called as drift velocity. Now next, what does the conductivity of metal depend upon? So conductivity property, it is not just a function of electrons, but it is also because it depends upon how many number of valence electrons are present in the valence band. And defining drift velocity, just now I told you that average velocity gained by free electrons in a metal when we apply electric field, where electrons start moving in one particular direction, is nothing but drift velocity. The next is relaxation time. Here, as we know that when we consider free electrons in a metal, they are moving in all possible directions, they are colliding with each other. Then what is the time taken between two successive collisions, or time taken? Of course, here, suppose what we are going to observe here is when we take a graph between time and of course, when we talk about velocity, which is drift velocity, we know that this is our velocity gained by electron. With the time, this drift velocity it is going to decrease, and there exists one particular time known as relaxation time. And at this relaxation time, drift velocity it is going to decrease by 1 by e value, 1 by e of its initial value, that is called as relaxation time. Then collision time, which is time taken between two successive collisions, and distance traveled between two successive collisions, it is called as mean free path. And all these definitions, they'll come from classical free electron theory. And coming to two success, what are the two major successes of classical free electron theory? It can verify Ohm's law. It also explains about electrical conductivity of metals, but when we talk about its drawbacks, it could not explain certain phenomena like photoelectric effect, Compton effect, and black body radiation. And also it could not, of course, it talks about metal, it talks about number of free electrons, but when it comes to conductivity, other solid materials, conductivity properties like insulators and semiconductors, classical theory is failing. Then after classical theory, we have our quantum theory. And when we talk about quantum theory, here completely we talk about quantization of energy, where we say that all energies are not possible, only certain particular values of energies are possible, which are called as discrete energy levels. So here when we talk about quantum theory, so here we talk in terms of course, Fermi ions and bosons. And here also we talk about Pauli's exclusion principle. And next is mobility. So once we apply electric field to free electrons, as we said that they are going to move in one particular direction. So when we talk about mobility, which is generally defined as mu, it is taken as drift velocity per unit electric field. Then talking about electrical conductivity is how much current is being flown per unit area per unit time. Then thermal conductivity is the amount of heat flowing per unit area per unit time of temperature gradient. Here this is electrical conductivity is with respect to potential gradient, whereas thermal conductivity it is with respect to temperature gradient. Now here coming to different theories of metals, we have classical theory, quantum theory, and band theory. And here how classical free electron theory failed to account for specific heat of solids. So according to our classical free electron theory, the experimental and theoretical values of specific heats of values do not match. So that's why it has failed. And then what are the factors? So coming to our last definitions, what are the factors that are going to affect electrical resistivity of materials? So these are the factors. Electrical resistivity of materials, it is going to be dependent on temperature, impurities, imperfections, magnetic field, pressure, as well as strain. Now next, talking about the basic assumptions of zone theory. Here zone theory, it talks about potential barriers, and it also talks about electrons moving in a periodic potential, and those potential boxes, they are separated by potential barriers. And then what are the drawbacks of quantum free electron theory? So it is not able to explain why some crystals have metallic properties and others do not have, and also it failed to explain why atomic arrays in crystal, including metals, should prefer certain structures, not others. Then when we talk about electron theory, in the end, of course, it talks about behavior of electrons, whether they are acting as bound electron or free electron. That is going to determine nature of the materials. So I hope that by taking all these terms and definitions, it is going to help us understand about semiconductor devices better. So with this, I'm going to end my session here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.